So today we study about projectile motion. Projectile motion is a very important example of motion in a plane with a constant acceleration. That's where the importance lies, because this motion is a two-dimensional motion with acceleration of the body being constant. So today let us study projectile motion. So what is a projectile? We say that when a particle is thrown upward making a certain angle with the horizontal, let's say with the earth's surface, and the particle moves in such a way so that it always stays near to the earth's surface. It never goes beyond a certain limit, so that the earth's force of gravity on the particle can be considered constant throughout. In that case, it is found that the particle takes a curved path as it falls down back to the earth after reaching a certain maximum height. Such a particle is called a projectile, and the motion that it undergoes is called a projectile motion. So, in case we assume that the air resistance throughout the motion of the particle is absent, then the only force that acts on the particle throughout its motion will be the earth's gravity, mg, that acts in the vertically downward direction, due to which the acceleration of such a particle is always in the downward direction and having a constant value g, right, which we know is equal to 9.8 meter per second squared, and this remains constant throughout. So, do we see that the acceleration that a projectile undergoes is a constant? In fact, we know its direction also. We know that it is always acting in the vertically downward direction. Along the horizontal, there is no acceleration. Acceleration along the x direction is 0. Acceleration along the y direction is g in the downward direction. So, before we proceed towards studying it in detail, let us first familiarize ourselves with some technical terms that we are going to use here. So, I have drawn the figure here for a projectile which moves in this curved path having projected from the point O. O is the starting point. So, O here is called the point of projection. Point of projection, the point where from where the projectile is projected. The angle theta that the initial velocity direction makes with the horizontal, I have shown here the initial velocity vector u, which is drawn as a tangent to the curve right at the starting position, right, and the angle that this initial velocity vector u makes with the horizontal direction is called the angle of projection. Theta is the angle of projection. Also, the as the projectile moves, it will take this curve that we have mentioned as OAB. As it goes up, it will reach a highest point that is mentioned here as A. At A, it will take a downward turn. So, A is the highest point of its motion, and then it reaches back to the ground from where it was projected. On the ground, it now falls off at a point B. So, the horizontal displacement of the projectile here, as we see, will be the displacement OB. The length OB here is called the horizontal range of the projectile. Horizontal range. Okay. And the time that the projectile takes to cover this whole distance as it moves from O to B is called the time of flight. So, T we take as the time of flight, the time for which the projectile was in air. Then we also take up the height of the point A as the maximum height attained by the projectile, right. So, if we consider the distance of the point A from the ground as this, we call it capital H. Capital H is called the maximum height. Fine. So, to study a projectile motion, what we do is we split the motion of a projectile along two mutually perpendicular directions, the x and the y axis. We have seen in the previous video that when a body moves in a plane, its x and y directional motions can be split along x and the y axis separately, and these two motions are independent of each other. So, the same thing we are going to do here also. While we do that, we consider the point O, which is the point of projection, as the origin, and we assume, let's say, that the particle is projected at t is equal to 0, starting time is t is equal to 0, and the plane in which the particle moves, the plane of motion, is the xy plane. Okay, we take the horizontal line along the x axis, the vertical line along the y axis, and we consider the vertically upward direction as along the positive y axis. So, this is along the horizontal along the x axis, and the vertical direction is along the y axis. Now, look at a few things here. See that the initial velocity vector u, this is the initial velocity, this is a constant, right? The velocity with which the body would be projected, that velocity once given to the particle, that is what it has as its initial velocity. Of course, that velocity will change as the projectile moves. The angle of projection is also a constant. Once the angle has been decided, after that, that is the angle with which the particle is projected. So, when we try to study these the motion of this projectile together, we shall be using these quantities as constant quantities. U, initial velocity, is one constant, theta, the angle of projection, is another constant, right? And now, as we try to split the motion along two perpendicular directions along the x and the y axis, we can take the components of the initial velocity vector u, which, as you can see in the figure here, the initial velocity component of u along the x direction will be this length ux, which from vectors we understand will be nothing but u cos theta, whereas the initial velocity vector's component along the y direction, which will be this uy, will be u sin theta. So, uy will be equal to u sin theta. Also, we know that the acceleration along the x direction is 0, whereas the acceleration along the y direction, understand that it is in the vertically downward direction. So, if we have to take it along with the sign, we will take it as minus g, right. So, these are the two set of values that we have along the x and the y direction. We say that both the accelerations are constant here. Along the x axis it is a 0, along the y direction it is minus g, both are constants, and hence we can use the equations of motion while studying a projectile motion. We can in fact use equations of motion along both the x as well as the y direction. So, we consider the x directional motion here, let us say, and the y directional motion over here, and now let us write our equations of motion along these two directions, and then we will proceed. So, the first equation of motion, when we use it along the x axis, what do we get? We will get Vx is equal to ux plus ax into t, right. Since ax is 0, the acceleration of the projectile along the x direction is 0, the second term will go to 0, and we will have Vx is equal to ux. What does that tell us? That tells us that the projectile has a constant velocity along the x axis, which is u cos theta. The component of velocity along the x direction does not change with time, it remains the same. If we try to see this in the figure above, what this would mean is, as this projectile moves and we try to draw different velocity vectors throughout its motion, some v over here, some v dash over here, right. In all these cases, the horizontal component of this velocity, that will be Vx over here, and let us say Vx dash over here, all of these we can see that they will come out to be equal to ux, telling us that along the x axis the projectile has no change in speed. It moves with a uniform motion along the x axis, right. So, this is what this first equation of motion along the x axis is telling us. Let us number this equation, let us call it equation number 1. If we use the second equation of motion along the x axis now, s is equal to ut plus half at squared. Along the x axis, the displacement can be written as x itself. So, x is equal to uxt plus half axt squared. Again, since ax is 0, the second term of this equation will also go to 0, and we will get x is equal to ux into t, which is an equation of the form displacement is equal to velocity into time, or distance is equal to speed into time, the equation that we have for uniform motion when a particle moves with a uniform speed, right. So, see that because we have now understood that along the x direction the motion is really a uniform motion, that is why we are getting such an equation, and we can write it as u cos theta into t as the value of x at any point in time. Let us number this equation as equation number 2. Okay. We will also try to use the third equation of motion along the x axis, though we shall see that that equation does not give us anything new here. The third equation is v squared minus u squared is equal to 2ax, which along the x axis will be vx squared minus ux squared is equal to 2ax into x. Since ax is 0, this term will go to 0, and this gives us vx squared is equal to ux squared, which is nothing but vx is equal to ux, which is the same as equation number 1. So, we are not getting anything new here from the third equation, so we will just neglect it. Now, let us move along the y axis. Along the y axis now, when we try to write the three equations, the first equation of motion, vy is equal to uy plus ay into t, where uy is u sin theta, ay is minus g and into t. So, the equation that we are getting here is vy is equal to u sin theta minus gt. This gives us the variation of velocity along the y direction with time. See that as time increases here in this equation, this factor with a minus sign keeps on increasing, thereby decreasing the value of vy continuously. So, we say that as time increases, the y component of the velocity of the projectile keeps on decreasing. How do we understand here in the figure? See, the initial y component is this uy. Now, when the particle reaches to the next point that we have, where we have drawn the velocity vector v, see that if I try to draw the velocity component along the y direction, it will be only this much smaller than uy, isn't it? In fact, if you try to look at the point A, the point A is the highest point where if I try to draw the tangent which will give me the direction of velocity, that tangent will actually be along the horizontal, isn't it? Like this, telling us that there is no velocity with the projectile at the highest point. All the velocity is along the x direction. So, at the highest point, the velocity along the y direction goes to 0, and thereafter as time further progresses, at the next point, if I try to draw the velocity component along the y direction, it will actually come out to be negative in the downward direction, vy dash. And so, we see that now the velocity of the projectile along the y direction is pointing in the downward direction, and as we proceed further, we can see that here at the point B actually it will have a even greater value of vy in the downward direction. So, that means that the velocity along the y direction keeps on decreasing from the starting position, reaches a 0 value at the point A, and after A it becomes negative and it starts increasing in the negative direction. Okay. So, we can number this equation, let us call it equation number 3. The next equation of motion now, s is equal to ut plus half at squared along the y direction will be y is equal to uyt plus half ayt squared. When we substitute the values, we will have u sin theta t minus half gt squared, which is a slightly more involved equation, a complex one containing linear as well as quadratic terms in t. So, we can just keep it like that, u sin theta t minus half gt squared, and give it another number, let us call it equation number 4. And now the third equation of motion along the y direction, v squared minus u squared is equal to 2as will give us vy squared minus uy squared is equal to twice of ay into y. Taking uy squared on the other side of the equality will give us uy squared plus 2ay into y, and when we substitute the values, we will have vy squared is equal to uy, which is u sin theta. So, u squared sin squared theta minus, why minus? Because ay is minus g. So, the plus sign here will become negative. So, it will be minus 2gy, right. So, this is an equation that connects the velocity along the y direction with the y directional displacement y. See that all the other terms here are constant. U is a constant, theta is a constant, g is a constant. So, this equation connects Vy with y, right. This is how we have all the other equations connecting various quantities. Let us call this equation as equation number 5. So, what we have done just now is we have use the equations of motion along both the x and the y directions, and we have got 5 equations here through which we can now try to find out other things, other aspects related to this projectile. So, what all aspects shall we look for? We shall look forward to find out, let us say, the horizontal range of the projectile, the time of flight of the projectile, and the maximum height of the projectile in terms of u, theta and g, all 3 of which are constants now, right. So, let us do that one by one. So, we shall be using these equations, one of these 5 equations that we have, and we shall be substituting some condition in these equations to get our required value. So, we start with trying to find out the time of flight. The time of flight, written as capital T, which is the total time that the projectile takes to reach back to the ground after being projected from the point O. So, this is the projectile, right. It starts from O and reaches back to the ground at point B. See that when it reaches to the ground, there its y directional displacement becomes 0. Between the point O and B, anywhere when it is in air not touching the ground, it will have some non-zero y directional displacement, but once it reaches back to the ground at the point B, its y directional displacement will once again become 0. So, if we can find out some equation out of these 5 which connects the y directional displacement of the projectile with the time, then we can use that equation to get the time of flight. So, if you just go through these equations carefully, you will see that it is the equation number 4, y is equal to u sin theta t minus half gt squared, that connects the y directional displacement with the time, right. And what we can do is we can substitute, put y is equal to 0 in equation number 4 to get that time at which y directional displacement becomes 0, right. And that is, we know that at the final position the y directional displacement of the projectile is 0, right. So, what does this equation give us? The equation is y is equal to u sin theta t minus half gt squared, right. So, when we put y is equal to 0 here, see that we will get 0 is equal to u sin theta t minus half gt squared. We can take a t common on the right hand side here and we get t into u sin theta minus half gt, and what we are getting from here is these two factors have their product equal to 0. What is the meaning of this? The meaning of this statement is that either t is equal to 0, the first factor is 0, or the second factor is 0, which means u sin theta minus half gt is 0. When any of these two equations is true, we will have the product of these two terms as 0, isn't it? So, the second equation is actually giving us t is equal to, if you just solve this, this will come out to be 2 u sin theta by g. This is the second t value that we are getting. First t value is t is equal to 0, second t value is t is equal to 2 u sin theta by g. Now, which one is our answer? Which one is the time of flight here? Let us understand both the answers. The first answer is telling us that at t is equal to 0, the y displacement is 0. Let us go back to the figure. Do we see that t is equal to 0 is the time when the projectile was projected? It was indeed projected from the ground, and at that point it indeed had a y displacement 0, right? That is the starting point of the motion. So, do we understand that this is a trivial solution? We know that at t is equal to 0, y is supposed to be 0, but that is the initial position, that is the initial time of starting of the motion. What we are looking for is the time when the projectile once again gets back to the ground, which then should be this value of time, right. So, we say that it is this answer that we are looking for, and this answer gives us the time of flight. So, we say that capital T, time of flight that we are looking for, is 2u sin theta by g. So, this is an important result. In fact, we remember this result and we use it into questions directly. The next term that we try to obtain here is the horizontal range. Horizontal range denoted by capital R. So, what is the horizontal range here? As already expressed, horizontal range is the horizontal displacement of the projectile when it reaches back to the ground. It is the length OB, as we see here in the figure. It is this length R from O to B, isn't it? Do we see that this horizontal range is nothing but the x directional displacement of the projectile once it has just completed its journey, once it has reached back to the ground? We know the time that it takes to reach back to the ground. So, if we know the time and we know the velocity with which it travels along the x-axis, ux, can we find out the displacement along the x direction, r? See which equation will help us. We are saying that we know the time in which it reaches back and we know the velocity with which it has travelled towards right along the x direction. So, do you see that it is the second equation of motion along the x-axis, x is equal to u cos theta into t, which will give us the x directional displacement in a time capital T, which is what we are looking for. That is the horizontal range, right. So, what we do is, in equation number 2, we put t, small t, is equal to the time of flight, capital T, in equation number 2. See what it gives us? X is equal to u cos theta into capital T. Understand that when we put capital T over here, this x will become r, the horizontal range now. So, this gives us r is equal to u cos theta into what is capital T, the time of flight, we have just now obtained it, 2u sin theta by g. Let us solve it. R is equal to u squared into 2 sin theta cos theta by g. See that this can also be written as r is equal to u squared sin 2 theta by g, because we know that 2 sin theta cos theta is nothing but sin 2 theta. So, this becomes our next formula to be remembered for horizontal range, u squared sin 2 theta by g. Next expression will be for maximum height attained by the projectile, maximum height, we call it capital H. So, as we have already seen in the figure, the maximum height is the distance of the point A from the ground, the vertical distance. What happens at the point A is the projectile loses all of its y directional velocity. It has only x directional velocity remaining with it. So, the y directional velocity goes to 0, and what we are looking for is the y directional displacement of the projectile at that point. See that maximum height of the projectile, which is the height of the point A from the ground, is nothing but the y directional displacement of the projectile when it is at the point A, isn't it so? So, which equation out of these 5 equations connects the y directional velocity with its y directional displacement? See that it is equation number 5. Equation 5 connects y directional velocity with y directional displacement. So, what we do here is we put y directional velocity 0 and find out correspondingly the y directional displacement, which will give us the maximum height. So, what we do here is we put Vy is equal to 0 in equation number 5, right. Equation number 5 is Vy squared is equal to u squared sin squared theta minus 2gy. So, when we put Vy is equal to 0, we get 0 is equal to u squared sine squared theta minus 2gy, and from here we can get the value of y as u squared sine squared theta by 2g, which understand is nothing but the value of h. Maximum height is the same as the y directional displacement at that point. U squared sine squared theta by 2g then becomes the formula for the maximum height attained by the projectile. This is the third formula to be remembered, to be by-hearted for a projectile motion. Okay. We can also see something else. At the maximum height, if we use the first equation of motion along the y direction, Vy is equal to u sine theta minus gt. See that when Vy it becomes 0, this gives us t is equal to u sine theta by g. And if you just pay attention to this value is just half of capital T by 2, so just half of capital T, it's just half of the time of flight. The time of flight was 2u sine theta by g. That tells us that the projectile takes half the total time to reach the highest point, and in the next half time it comes back to the ground from the point A to the point B. So, the time taken from O to A is the same as the time taken to move from A to B, which tells us that the motion of this projectile is actually symmetric about the point A. In fact, if we take this vertical line passing through the point A, then the whole path of the projectile can be proved to be symmetric. The left half of the path is a mirror image of the right hand of the path, right hand side of the curve that you see here. It can easily be proved. Okay. Now, the next thing that we look at here is one more equation that we would like to find out, which is called the equation of trajectory. What is the equation of trajectory? Equation of trajectory is actually the equation of the path or the curve traversed by the projectile. So, what is this? If we go back to the figure that we have drawn here, the equation of trajectory is nothing but the equation of this particular curve that we have drawn for the projectile. The path that the projectile takes in the xy plane, the equation of that path is the equation of trajectory. So, as we look at this figure here, we understand that the equation of trajectory should be an equation that connects the x and the y coordinates of the projectile, right? So that if we substitute any value of x in that equation, we are able to get the y coordinate of the projectile at that particular point, right? So, we know what coordinates does the projectile passes through. So, how do we get the equation of trajectory? We can once again take the help of these equations that we have. See that here equation number 2 and equation number 4 connects the x and the y displacements with time. Let me write these equations here once again. Equation number 2 is x is equal to u cos theta into t, whereas the fourth equation is y is equal to u sin theta t minus half gt squared. X as a function of t and y as a function of t. Now, from these two equations, if we want to find out y as a function of x, what we can do is we can find out the value of t from the first equation. T is equal to x by u cos theta. See that this is what we will get for t, and then we substitute this value of t here in this equation in both the terms that we have here, so that we get an equation in y and x. Let us do that. This implies y is equal to u sin theta into t is x by u cos theta minus half g into t squared, means x by u cos theta whole squared. We can simplify this equation now. This gives us y is equal to, see that u cancels out, sin theta by cos theta can be written as tan theta. So, we get x tan theta minus half g into x squared by u squared cos squared theta. This is the equation that we are looking for, the equation of trajectory. See that this equation connects the x coordinate and the y coordinate together, you put any value of x over here and you get the corresponding value of y. So, on the projectile, the path that the projectile takes, like this, you put any value of x and you get corresponding value of y. So, that the coordinates of that point will be x comma y, isn't it? Like this. In fact, if we go back to the original figure, there is an interesting task that you can do with the equation of trajectory. Do you see that the point A will have an x coordinate of r by 2? This lies just in the middle of the total horizontal range, isn't it? So, can we say this point is at r by 2, half the horizontal range, and the y coordinate of the point A is nothing but the maximum height h. So, what you can try doing is you can put x is equal to r by 2 in the equation of trajectory and check that the y value corresponding to that comes out to be h, isn't it? Or you put x is equal to r, which corresponds to the point B, and you see that you get the y value to be 0. These are just some exercises that you can do with the equation of trajectory just to see how it works. Next, we shall look at a few examples on projectile motion and familiarize ourselves with this topic a little more.